Let's go into a little bit more depth on Hive and some of the more advanced features of it and some of the nuances of how it actually works. We're not going to go into a lot of hands-on examples here. I mean, I could do a whole course on Hive easily, but just want you to know about some of this stuff so you have it in the back of your head and you can look up how to do these things if you need to in the future. So one of the basic concepts of Hive is something called schema on read, and this is what separates it from a more traditional database. So with a real relational database, it uses something called schema on write, where you define the schema of your database before you load the data into it, and it's actually enforced at the time that you write the data to disk. Hive flips that on its head. So it takes unstructured data and just sort of applies a schema to it as it's being read instead. So your data is still stored as just, tab delimited text files or whatever it might be, with no actual structure to it, no actual information about what kind of data that represents. But Hive maintains a metastore, is what it's called, of the actual schema data that's associated with that unstructured data. So that's what tells it how to actually interpret those raw text files. So that's called schema on read, and there's actually a separate product called hcatalog that can expose that schema to other services as well. So here's an example of it. So if we kind of cheated in our previous example here where we used the Ambara UI to import our data through a graphical user interface, but if you wanted to do it the hard way, it would look something like this. So you'd enter a command called create table ratings, and it will give you the various field names and their types. They all happen to be integers in this case. And then you give it, how that data is actually structured on disk. So the row format is delimited with tab delimiters stored as a text file. And that is basically defining the schema that we will apply when the data is read as opposed to when the data was written. So the data was already written in a very unstructured tab delimited format. This create table command is just creating a schema in the metastore that gets applied to that data once it gets read into Hive. So to do that from a command line interface, we would do something like load data local in path. This is a way to refer to your home directory under Hive /ml100k/u.data. Okay, and we will overwrite that into a table called ratings. So that's what's happening under the hood. Okay, when we do that, basically we're defining a schema on read that's applied to data that's already been written in an unstructured data. And it just keeps it in that format. So, Hive isn't, going and, creating some structured relational database under the hood. That would be pretty inefficient when we're talking about big data, right? So it's just taking the existing data that you have on your cluster and imparting a schema to it when it's read in. Where does that data actually live? Well, this can get a little bit complicated and a little bit confusing. So when you do a load data command from the CLI, command line interface, that's actually going to move data from a distributed file system into Hive. So basically we're saying with load data, we want Hive to manage this data from now on, and it's going to take ownership of it and move it into Hive itself. Reason being that if you have a massive data set on a distributed file system, odds are you don't really want another copy of it. Okay, so Hive is just going to move that to where Hive expects it to be, and Hive will take ownership of that data from now on. Okay, now again, it's not actually reformatting it into some fancy structured format. All it's doing is keeping that schema information in its metastore. Okay, it's just moving the raw data from one place to another. Now, in contrast, load data local will actually do a copy. So if you're actually loading data from a local file system into Hive, load data local will do that, and that will leave your original data untouched. But again, that's assuming that you're reloading it from a local file system and not a distributed file system. So the implicit assumption there is that we're not dealing with big data there, because you could actually fit it on your local file system. So we say, okay, we'll just make a copy. That way you don't have to worry about it. And further confusing matters is the idea of managed versus external tables. So these are examples of managed tables where Hive is taking ownership of the data ultimately, and its copy of that data or the data that it moved into Hive is going to be owned by Hive. So if you do a drop table command from Hive, that data is gone, okay? In this case here. But sometimes you want to share that data with other systems that outside of Hive. So that's where external tables come in. And all it really means is that when you create your table, you just say create external table, give it the format that it's in again, and you give it an explicit location of where that data lives. So create external table with location says, I'm going to use Hive on this data here, but I'm not going to really own it anymore. Okay, so if I drop this table, if I drop ratings, it's going to drop the metadata, but it's going to keep this data intact, and it's not going to mess with it. It's just going to leave it there. Okay, so external tables really just means that Hive doesn't take ownership of it, and when you drop it, the data is still retained and it doesn't move the data around. So if you need to share your data with other systems, that's an easy way to do it. That's really the only difference between managed and external tables. I mean, remember that Hive isn't really messing with the raw data itself. So it's really more a question of who owns the data and who's actually responsible for deleting it when you're done. Okay? Another important topic with Hive is partitioning. So if you do have a massive data set and your queries tend to be on a specific partition of that data, partitioning in Hive can actually be a very important optimization. So for example, let's say you have a customer's database that consists of names and addresses. Maybe that's going to be partitioned by country. So if you say partitioned by country string, that treats country as just another column, but it's not really a column under the hood. The country column will become basically part of a subdirectory under where Hive stores this data. So it would actually have a structure like this for a table named customers. It might be customers slash country equals CA slash, and that's the actual path there, okay? So the partitions are sort of these little expressions here of what that partition is and the actual partition within it. And you can actually chain these together if you have more than one partition. Maybe you'd have country equals CA slash province equals Alberta or something, right? So that's how partitioning works. Very powerful if you're going to be doing queries that are specific to a given partition. So if my usual usage is to only query for information on countries in a specific country, this would make a lot of sense. Okay, it would save a lot of time because we wouldn't have to scan over the entire customer database. We could just scan over the actual files that are specific to the country that I'm interested in. Another quick note here. Another interesting thing about Hive is that you're not restricted to just the usual data types of integers and strings and bytes and whatnot. You can also do more structured things. So this is an example of a struct, a structure called address that contains a street string, a city string, a state string, and a zip integer. So you can actually store structured data within Hive databases. So the flat nature of the denormalized nature of Hive makes that possible. You can also store maps as well. Okay, kind of a neat little trick. There are many ways of using Hive. We've looked at using it through Ambari, and if you're on Cloudera, you might be using Hue instead. But there's also a Hive prompt. If you just type in Hive from your cluster, you can just get a prompt and type in those commands one line at a time interactively, just like you would with a database, right? You can also save your query files off to a file. So if you just type hive-f to the path to your query file, that will execute it one at a time. And through Ambari, you might have noticed that there was a save as command there that we could have used to actually save that script to a file. And if you wanted to rerun it from the command line, you could do it that way. Hive also contains a JDBC and ODBC server, so you can actually connect to it just like you would any other database through whatever systems or tools you may have. And it also exposes a thrift service. So this is actually a little service that Hive can run that lets you talk to it through, websites or web clients or what have you. Remember, however, Hive is not suitable for online transaction processing, so it's not really meant for being hit with tons of queries all at once, from a website or something like that. That's where you use something like HBase instead. Okay, but it does provide a way of using Hive, and more often it's used to actually keep Hive running on one instance of your cluster instead of every instance, and that thrift service provides sort of an interface between the rest of your cluster and the Hive service. You can also manage it through Oozie, which we'll talk about later in the course. Oozie is a management tool for your cluster as a whole that lets you schedule more complicated jobs across your Hadoop cluster. That's Hive in a nutshell. So up next, let's actually practice what you've learned, and I'll give you a little challenge exercise to get your hands dirty with Hive.